coming even more and more smarter products. So we have here increased complexities. We have almost autonomous driving cars. We have intelligence in our smartphones, in industrial processing. So we have a lot of new features, and this software is very hard to program and usually also has hard requirements. So we have real-time requirements. We need the execution be finished in a very short time, or we need to be able to analyze how long it is running. And we require low power consumption for these because oftentimes we have mobile applications. The solutions from the hardware vendors are heterogeneous multi-core processors. What do we mean with that? So we have multi or many core processors, something like an ARM processor here with 4 homogeneous cores, but also something like a system from Calray where we have more than 200 cores. So these would be many core processors. But now the current trend is we also have special accelerators, something like the NVIDIA Jetson TX2 has a GPU on it, so a graphics processing unit. We also have digital signal processors. These are accelerators that are more efficient in calculating or in processing specific kinds of applications. So in these cases, usually data-driven applications. These new systems deliver higher performance than the classic single core processors. They can process more efficiently with a lower power reduction, the lower power consumption. And they can also be used to run multiple algorithms and applications in parallel. So it doesn't have to be only one application that is running in parallel, but we can run 10 applications in parallel. And this new hardware also offers some kind of safety through redundancy. So this is something that is often used for these Infineon Oryx cores processors. We have 3 cores, and a very common use case is to have 2 cores executing or processing the same algorithm and then comparing the results just to be sure that the processor is still okay. But parallel hardware needs parallel software. We just have a look at the theoretical application performance starting from a single core processor, going to a multi-core processor or to a heterogeneous many-core processor. We can see that it's ever increasing, but here already starting with the multi-core processors, we come to a gap. So if we don't parallelize our code, we get a bit of performance, usually by small optimizations in the architecture, but this is not really good. But if we look at if we are able to optimize our code, if we parallelize our code for the target platform, we get still a lot of performance out of these new architectures. And how is this done? So how are we doing it? We offer this emmtrix workflow. The idea is to start with your program. It could be in a model-based language like MATLAB or Simulink or Scilab, or directly in C code. And with the combination of emmtrix code generator and emmtrix parallel studio, you can generate parallel C code for different target platforms. So the most important one would be multi-core processors. So this would be directly C code. For architectures that have a GPU or a DSP, where we can use other languages like OpenCL or CUDA, we can generate code for that. And for FPGAs, here it's possible to use high-level synthesis, basically generating C code that can be used to configure the FPGA. And the idea is we start from emmtrix code generator, we have a sequential program, and with the help of emmtrix parallel studio, we can generate parallel C code. This is an overview of our tool. So it's a it's based on Eclipse. On the left side, we can see the workflow starting from the top. If we start from a model, we have here a part about sequential C code generation. This would be the integrated emmtrix code generator. We have some test steps in between, like here a sequential program test, parallel program test, and then we have the main part with the parallelization. In the main part of the Eclipse view, we can see different versions of the code or of our results. So at the top, we can see a model that was started here as the basis. In the middle, we can see a performance estimation. At the bottom here, we can see a schedule. This would be a result of the parallelization. This workflow is meant to be interactive. This means we start with the algorithms already implemented in the input languages. We use our Parallel Studio to do a first optimization. We present the results as a feedback to the user, and he controls the whole parallelization algorithm. So he's in charge of assigning, or he has the last say in assigning specific tasks to cores or to GPUs and stuff like that. So he stays in control over all major decisions of the parallelization process. So now let's talk about best practices. How do we get a parallel program? How do we optimize our algorithm for the specific target platform? The first critical part is to detect the critical parts of the application. Just a rule of thumb, 80% of time is spent on 20% of code. So this means if we want to optimize the application, you should focus on the 20% that matter. So you need to find out where most of the time in the application is spent. There are several ways to do that. Well, I've mentioned here are three most common ones. First one would be profiling. Profiling means we instrument the source code. This means adding some kind of instructions to start and stop a timer, and then we just measure the timing on the hardware. Depending on the hardware, it's also possible to use a special debug interface, so there is no real overhead for the time measurement. But even with the very basic hardware, it's usually possible to have some kind of hardware timer to measure the timing. This is the most accurate one for the actual performance on the hardware, but you actually need the hardware for that. So you need to compile your code and you need to execute it on that system. Simulation here has the advantage that you don't need the hardware. The idea is that you simulate a cycle accurate or a near cycle accurate model of the hardware and can then get performance for your application. Depending on the accuracy and the simulator, this might take quite a lot of time, but then so here you can make a trade-off. If you want to have really accurate number, you need a lot of time. If you only want a rough estimate where the hotspots of your application are, this this is something you can get faster. And lastly, even more abstract would be static code analysis. Here, the idea is that you can analyze the source code, just have a look at it. What kind of instructions are performed? Are there mathematical operations, so in addition, division, multiplication, and trying to find out where most of the time is spent. So indicators might be loops and stuff like that. But this can also be done in a more sophisticated way. So there are tools available that can analyze the source code together with an internal hardware model. Just to show you how important it is to know where the performance or where the hotspots of an application are. Here we have a screenshot of a deep learning neural network. It has 20 layers, and we basically know only that there are several function calls. Most of them look almost the same, and we don't have any performance information here. So we basically have only a lot of function calls. Some are dominated here by the for loop, but without any performance estimation, you don't really know what call, which of these calls should be optimized. If we add performance information, basically scaling the width of these blocks according to the runtime on the target platform, we can see that only 3 of these calls, maybe a 4th one that is also still quite short compared to the other ones. You can see that only 3 of them dominate the overall application. And if we want to optimize this application, we should focus first on these 3 function calls, maybe on the 4th one, but only after these first 3 have been optimized. So it's really vital to know your application and know where most of the time is spent when executing. In Parallel Studio, we use this kind of hierarchical program view. The idea is that we have on the x-axis the time. So the width of each block shows you the relative execution time compared to the blocks below it. And the y-axis shows the structure or the hierarchy of the program. Here we can have function calls, we have for loops, if blocks, everything that is part of a control structure. The data that is used for this performance estimation can come from different sources. The most basic one would be static analysis with a very abstract hardware model. Here the idea is only to find out the actual hotspots or critical parts of the program. If you want to have more accurate numbers, you can use tools like AIT or Timeweaver from Absinthe to get more accurate numbers and use these as the basis for the parallelization. If you have a look at control algorithms with our hierarchical program view, we can see these are can be more flat. This would be an application where these smaller blocks are usually assignments coming from some sensors, and we have here with these hierarchies with 3 or 4 layers, we have decisions. So basically if blocks that do something depending on the actual input data. You can see the program here looks quite different than the one before. Would have been an application from that would be an image processing algorithm. Here we have more, but these are usually more dominated by for loops. Now, if you know where the time is spent in your application, you have to identify the parallel parts of the program. So you need to know which parts of the program can basically be split up and executed in parallel. So the easiest parallelization technique would be looking at the task level. Here we can have a look at independent code parts in the program. We have to identify independent code parts. So if you have if we have our program code and we can split it up into several parts that are independent from each other. So we basically look at the data flow or the data dependencies. We can map them to different cores. So from this one task, we can split them up in 3 and assign the individual parts to specific cores. This comes with an overhead, so we can see the arrows here. Usually we either have to synchronize them. This means a core has to wait before he's able to take the data, or we have to explicitly send the data. This really depends on the target platform. If it's not as easy to split up the code, then task level pipelining can be an option. Here we need some prerequisites that have to be fulfilled. At first, the task has to be repeated in a loop, and then it can be split into subtasks that have about a similar length, and they depend on each other. You can see that here on the left side. We basically have now 3 different parts. The length is about the same. And now we are able to map them to different cores. If we just execute them now, this wouldn't be faster than the sequential one because we also have the dependency here. We have a communication overhead. But if we execute this in a loop, we are able to basically form a pipeline. And we can see after 3 steps, this pipeline here would be full. All 3 cores would be doing something in parallel. The parallel work here doesn't, it increases the throughput of the application, but the delay is still the same. So from the start of the first iteration until the end of the first iteration, it takes about the same amount of time like in the sequential case. But with this overlapping execution, we still get a lot of speed up. This detection of parallel tasks is handled automatically in Parallel Studio. You can see here down below several tasks. So the width is still the duration of a task. If we select one, we can see the dependencies highlighted. So the result of this one task is used on several other cores, but the communication is already taken into account. So here we can basically see a pre-parallelized program, and all these dependencies are taken into account, and we still get speed up. The tasks we show here are usually either code blocks, so these would be basic blocks, so just blocks that have statements inside them, but it could also be special blocks like function calls or for loops. So here you can see a for loop. Now, this definition of tasks might be limited, and yeah, if it's not possible to just split up the code into independent tasks, then we have to increase parallelism. Increasing parallelism is not always possible, but what we mean by that is to use code transformations to make the intrinsic parallelism usable. Let's have a look at an example. This would be a simple matrix multiplication. Consists of, it's composed here out of 3 for loops. These are nested, and the result is then written into an array, the name C. By our definition of tasks, one task would be the outer for loop, the next task would be the next for loop. Here would be one basic block with an assignment. Here is another for loop, and basically a basic block with a statement. And just by looking at it, so if we look at this abstraction layer, we don't have any potential for parallel execution because we have to execute. So we only access specific data, and then this result is written into that array. So it's not possible to do it to do a parallelization on task level directly with this code. What is possible is to do a code transformation, a loop transformation here with a variable splitting. So instead of having only one matrix with the C, one variable for the results C, we insert C0 and C1, and we perform a loop splitting. We basically duplicate the for loop, but we change the boundaries of this loop, of the loops. So instead of going from 0 to 10, we have one from 0 to 5, and then one from 5 to 10. And now we have basically 2 for loops, the outer for loops, that can be executed in parallel. We can calculate C0 and C1, and later on just collect all the results. Then we have a parallel program. This is something that is automated when you use emmtrix Parallel Studio. For instance, if you have here a for block, you can just right-click on it, can select a transformation, and if loop split would here be splitting a for loop that has an if block inside of it to generate 2 independent or multiple independent for loops that only cover the parts that are that are different in respect to the if block. And just so in our tool, you basically only have to select them, can press apply, and they will change the code. And depending on the input code, this might lead to more tasks that can be executed in parallel. But there are also other steps for better parallelization. When we look at the algorithmic level of an application, where we can just use a different implementation of the same functionality. So one idea would be here, if you look at sorting algorithms, the basic functionality of a sorting algorithm is the same. So you have a specific amount of data and several objects, and you want to sort them in a specific order. In an order. And depending on the actual algorithm and implementation that you select, you might select something that is more applicable for parallelization than not. So one example would be here, instead of quicksort, you can use hyper quicksort, and just by the overall structure of the program, hyper quicksort is better fit for parallelization. But it's also possible to exploit characteristics of an algorithm. One example here would be a fast Fourier transform. And here it's possible, instead of having one endpoint FFT, you can use two n-half point FFTs. So this is just some characteristic of the algorithm. And now it's possible to basically perform the FFT in parallel, and then you get a small overhead just to collect the data, the results again. This parallelization on algorithmic level is integrated in emmtrix ParaStudio just by the use of MATLAB or models as an abstraction layer, because usually it's quite hard to detect an algorithm automatically from source code. So just looking at the source code, detecting that it's a sorting algorithm, that's not really possible. But by using a more abstract representation, like MATLAB or other model-based language, there are a lot of already pre-implemented algorithms, and they can be detected very easily. And here in this case, we know it's an FFT, and we can just optimize it for a specific number of cores, can press apply, and it will regenerate the code and split it up into 4 independent parts. Only inserting or increasing the number of tasks is not enough. The overhead comes from the synchronization of the execution, and this is a very important topic. Usually we need some kind of data exchange or synchronization, and deciding when and where to communicate has a lot of other side effects. So first of all, it influences the memory allocation per core. So if we have basically the option to send it before or after other executions, we have to assign the memory on the specific core. But this is not the most crucial topic. The important part is that a wrong placement may cause execution errors. So these are errors like race conditions. So what is a race condition? Race condition means the result of an operation depends on the timing of other operations. We will have a look at that. We have this intended behavior. We have one shared variable, and we have 2 cores that should just add number 1 to that variable. And basically we start with a 0, and if both cores have added their 1, we should get a 2 in the end. But here we have to take into account that just adding one number is not one single operation. In this simple example, it might consist of 3 steps. On an actual hardware, this might be even more steps. And if we just have a look at, okay, core 1 is doing its task, then core 2 is doing its task, then we get the correct result. But in the case of a race condition, it might happen that the execution here is overlapped. So while core 1 is still performing its processing stuff, the processing, core 2 already starts the same thing. And when core 2 is reading the value, it's reading value 0. If it adds 1, it has the 1 as a result, and in the end, both of them write the value 1 back into the shared memory. And this means, in the end, we have the wrong result here. And the timing between these two cores is really hard to debug. If you really have an application that has this kind of behavior, it's hard to pinpoint the actual part, because breakpoints in a parallel program affect the timing. And if you have breakpoints on several cores, you might never get this problem. So these race conditions can be the reason why some programs just crash randomly when they run for a while. So it's very important here to insert the synchronization between the cores and to enforce the behavior that you want. So this parallel execution here is uncontrolled and can lead to errors. Another problem that might occur when you insert communication or synchronization are deadlocks. This is the case when a program basically, or a process, waits for data that never arrives. So basically we have a communication where the receiving side is waiting for data, but the sender is blocked by something else. So maybe he's also waiting for data, and yeah, then we have a deadlock where the program cannot continue. So here we have an example how this might happen. So in this case, we have two cores, core 1 and core 2, and we have two resources. Both of the cores want to access both resources, and in this, if you want to use it, you have to get exclusive access to the resource. So if core 1 is asking permission for resource 1, core 2 is asking permission for resource 2. Both of them are granted, and now both of them want the other resource. Basically, they want exclusive access to resource 2 or 1 from the other side. But exclusive access means only one core can access it. This is not possible. Now both cores are waiting, and the program has stopped from continuing. The cost of synchronization also has to be taken into account. So synchronization after every task without looking at the overhead might create a program like this. So it looks almost like a staircase. What we wanted is that on these 4 Cortex-A7 processors, that there is a parallel execution. So we assigned here these for loops to the different blocks, but we can see they are still executed one after the other, because it's very wastefully parallelized. So we have here a communication overhead. The cores wait until some processing here is performed on core 0. So everything here depends on core 0, and this is not a very good parallelization. So although all cores are used, they are never used at the same time, or almost never, so only here for very small parts. And this is not a very efficient parallelization. So the main part here is only insert synchronization when necessary. The synchronization insertion in emmtrix Parallel Studio is handled automatically. So communication is inserted where necessary. And this systematic approach ensures that there cannot be any race conditions inside of the code. We have this correct by design approach, and just by inserting the communication in specific parts of the code, it is ensured that no race conditions or deadlocks can occur. We are inserting explicit communication instructions. This means we have here directly send and wait and receive instructions. So really sending the data. The actual implementation is hardware dependent. So can use something like the POSIX standard for Linux-based operating systems, but it's also possible to just use shared memory or hardware network on chips that are available for sending data around between the cores. So summing up the recipe for a good parallelization, we have 4 main steps. First, you have to find out where your application uses a lot of time. So find the hotspots of your application and the parts of the code that should be optimized. Then you have to determine the dependencies of the individual parts of the code, of the tasks, and find the parallel potential. If this is not high enough, so if there are not enough tasks, then it's possible to just do a code transformation, if you're doing it automatically, or refactoring, rewriting the source code to be able to exploit more of the parallelism. And lastly, you have to ensure the correct execution of the parallel program by inserting the correct synchronization functionality, inserting the correct synchronization instruction inside the code. Now, if we have parallelized it, we should evaluate the results. Just having parallel C code with all of that is not really enough to be sure that the parallel program is really correct. You have to look for several key factors to find out about the performance of the parallel program. So important topics are something like load balance across all cores. If you look at the staircase-like parallelization, there is a very bad load balance because only one of the 4 cores is working at the same time. Then you really have to look at the overhead that comes from the synchronization and communication. This is not only the time spent for copying data, but also waiting time. So if the core is just waiting for data, this might also indicate a poor parallelization. Then it's also important to take into account how fast are the cores and accelerators that are available. So if we execute something on a GPU, how much faster is it? And other topics to consider are something like power saving modes of cores. So the modern processors are able to shut down or lower the frequencies of individual cores. And now if you have a parallel program where some of the cores are idle for some time, then there might be an overhead just to wake them up and help with the parallel processing. In Parallel Studio, we show the results in our hierarchical, in our scheduling view. The idea is that we show for each core of the target platform. Here we would have an Infineon Oryx system with 3 tri-core cores, which show them on the show the timing and the load of these cores. And here on the right side, we can see a sequential boundary. So this would be the duration of the sequential execution, and you can see that the parallelization like this, there is a speed up of 1.9 almost, and this also visualizes the communication overhead. So the orange colors here inside of these tasks indicate that there is a communication overhead required. And although we send around a lot of data in this case, the speed up can be achievable because it's lower than the actual performance or the actual duration for these tasks, execution time for these tasks. As an additional way to test the code, we have integrated an automated profiling and simulation capabilities into EPS. So it's possible to instrument the source code and directly send them to the hardware. This relies on hardware that is capable of something like SSH, so having some standard protocols. Then we can send over the data, get the results back, and visualize them inside of our tool. And also the deployment of this parallel software to the hardware can then be automated for the well-known functions, well-known target platforms. So what are the benefits of using emmtrix Parallel Studio or the emmtrix Parallel Studio workflow? So first of all, we have a lot of automation and assistance for the users. If we have a look at the workflows, we have the input and C code generation part. The conversion of models to C code is directly integrated, and this conversion is already optimized for the later parallelization. So the C code that is generated here is optimized for analyzability and parallel execution. Then we have integrated an automatic performance estimation. This usually, in the default case, it relies on static code analysis with an abstract hardware model to estimate the performance in the target platform. Then we have this interactive, iterative optimization step, the scheduling and mapping. Here we have an automatic algorithm that performs the parallelization. It presents the results, and users can apply code transformations, set constraints, just to optimize this parallelization and get direct results. And if the parallelization is good enough, then the automatic parallel code generation can generate parallel C code for the actual target platform. Using such a workflow reduces the test and verification effort. As I already mentioned, race conditions cannot even occur, so it's not just by inserting them in this systematic approach, they cannot occur in the parallel program that is generated by our program. The same is true for deadlocks, and this correct by design parallelization ensures that there are no additional sources of errors just for the parallelization of the program. If there are already some other issues in the original program, in the sequential program, they still might be available in the parallel program. The detailed knowledge of the target architecture is not required when you use Parallel Studio. Usually, when you want to optimize your program, you have to take into account a lot of stuff. So for instance, the number of cores, the memory subsystem. So it's vital to know whether each core has its own memory or if we have a shared memory that everyone is using. And it's also important to know how these cores are interconnected. So do we have a network? Are they communicating with the shared memory? Just by using our workflow, this is abstracted, and this information is already a part of our internal hardware model. The code can be reused very easily on different target platforms. The original source code doesn't have to be changed. Just by optimizing it here for an ARM processor or a DSP, you can just use your source code, apply the different steps that we defined to get efficient code. And if you want to switch to another one, basically you can reuse some parts of the parallelization, or at least use the knowledge how to efficiently program one of the target platforms to get very fast, better results for with the help of EPS. And on top of that, we enable a model-based workflow. This has a lot of advantages. The model, if you just program in a more abstract level, not directly in C code, but start with a model, you can really focus on implementing the functionality of the algorithm without thinking too much about the target platform. And just by the way we integrate our emmtrix code generator together with EPS, we are able to generate more efficient C code that can be used as the basis for the parallelization.
Okay, I think now we should probably give Oliver a chance to get something to drink and oil his vocal cords a little bit. This was the introductory, well, the basic part of how to tackle the problem of software parallelization. We gave you a recipe of a good software parallelization, and we've given you some of the advantages that an automated approach provides, something like the approach that we've taken in emmtrix Parallel Studio. We're now going to show you the tool in action. And I would like you to sort of maybe take a minute or two, think about what you've seen, and let me know whether this is what you expected or whether there is something that you didn't understand, or just think about what you've seen, whether it was too fast, too slow, too detailed, and just let me know whether there's something we need to change. I think one person has got a bit of a problem with the microphone. Ideally, do that with your just opening your microphones. Click on that microphone button so that you can talk to us. If you prefer, as we're recording this, you can also send me just a question in the chat. Yeah. So let me hear how it's been so far. So. Presentation was brilliant, excellent. Okay, thank you very much, Nikolai. Yeah, if I may, I just mention your name. That is great. Thank you very much. So hopefully this helps, not just a beginner. So that's very kind of you to say, Nikolai. There were a few other beginners, but maybe Gavaskar, you've been in this before, right? If you can hear me, yeah, you can.
Yes, sir. I'm attending the last webinar also.
Yeah. Okay. So it's a bit of a repetition. I think you had this newer version already. Now, with sort of the hindsight of having seen it before, is this something that helps you to understand what we're doing? Is this useful to you? Are there some suggestions? That's of course what we're after, of where we could spend a bit more time, or maybe we're taking too long. Are we talking too much about our product?
No. Actually, I was about to talk, but my internet was reconnecting. I don't know. And this is what I'm searching for. I wish to familiarize with it, but during the implementation, I am having some troubleshooting problems. Okay. I'm working on it, and okay. It will be more helpful for me. So I'm keenly listening to the
demonstration. Yeah. Okay. Yeah. Fair enough. Okay, well, thanks a lot for that. Anybody else? I think Amin, you had some issues with the audio now. Can you hear us all right? Is everything fine, or have you left again? I think he's actually been thrown out again. Oh, that's a pity. Okay. Anybody else? Doesn't seem to be the case. Remember, if you have got some comments to make or questions to ask, just open your microphone and stop the flow, or if you prefer, just send it via the chat. Thank you very much for your contributions. Let's go to the demonstration of the actual emmtrix Parallel Studio. Over to you, Oliver.
Okay, so let's have a look at what our tool can do. I have here a very simple application, but it really shows the usage of emmtrix Parallel Studio with the whole workflow. So this means we will also start here with a model, just to show you the advantages when you start with a model instead of C code. But as we generate C code in the middle, after the C code generation, the workflow is basically the same, whether you start from a model or from C code. So what we have here is a Sobel image processing filter. The idea is that this is a processing chain. We start here on the left part with a MATLAB function that basically reads in an image. Here in the main part, we have several blocks. So the larger ones are convolution filters, one in horizontal direction and one in vertical. Then we have some operations. So here there is a product, here is an add, gain, square root, so several mathematical operations. Okay. And at the end of the chain, we write out the image on the hard drive. In our tool, we only have a viewer for models. So this would be a Simulink model. And in our tool, you're only able to open it and look at it. So there are some additional information here in the properties view, but you're not able to change anything. So the actual implementation of the algorithm should happen in Simulink directly. Now, if we start our emmtrix code generator here, in this case, it will generate the MATLAB code. You can see there are also some additional information about GCC. This is part of our integration. And we generate C code, we execute the C code, and we are able to get performance numbers for the C code that are not statically available. So this means if we have a look at the generated C code, we have some additional pragmas, just some information about execution times of loops and stuff like that. For loops like this, where we basically start from 0 to 640, of course, this is very easy. This can be statically analyzed just by looking at the code. But in other cases, this boundary here might be limited by the input data, by a function call, or something like that. And just by integrating this automatic execution here on the development platform, we can basically get the numbers of execution for these for loops, or for if blocks, we can analyze how often the true and false parts of the application are executed. Our code generation here has a lot more information, just to showcase a bit of emmtrix code generator. If you have a look at the specific block, this convolution block is something that can directly be used inside of Simulink, so in the model. What is used for the conversion is an actual MATLAB script, and it is analyzed in how it is called. This means we have information here about the parameters the function is called with. You can see the variable a here has a size of 480 times 640, and also that the range of the values are from 0 to 255. So this could be an 8-bit variable could be used to save the data. And we can also see the modulo 1 operation has a remainder of 0. This means, yeah, integer values would be enough. The data type that is here mentioned, the double data type, this is the data type that is used in the model. And yeah, for the C code, a smaller one would be enough. You can also have a look at different statements here in the code. You can see here some would only be a scalar value, so size 1 by 1, but just by the calculation here, it could get a range from -infinite to +infinite. So a lot of information here visualized inside of an HTML report. This is just for the emmtrix code generator generating efficient C code for the parallelization. If you now have a look at this C code, the C code, as I mentioned already, these pragmas for the performance estimation, but all other stuff is also optimized for a good static analysis. This means it is the preferred way to express any kind of processing here are for loops with fixed boundaries. If we work with arrays of data, they are also multi-dimensional. So not only a one dimension and then then performing the index calculation in line, but really accessing it with nested for loops, like you would do it when you, well, like most the developers are doing it when they write code like this. We have additional information here. This would be a kill var. These are information about the actual liveness of data and helps the static analysis. So some parts cannot be analyzed statically, but the information is available during the code conversion. And if the data, if a pragma like this is not available, the parallelization always has to assume the worst case, so that a variable, for instance, needs to be overwritten or needs to be copied as a whole array. With information like this, it is already known that some parts of the code are not required. But now let's go to our parallelization. So the first step of our recipe was to get a performance estimation. The performance estimation is performed automatically. We can also see some warnings here from the performance estimation. We are using emmtrix image read and image write functionality just for reading and writing the input file. This is not the most important one for the actual application. So we don't have a value here for that, but it's possible to add this number if required. So we can add this for the specific target platform and basically just assign a number to that execution time, or we can provide the source code so that it can be analyzed. Now, I mentioned already that we have here a hierarchical program overview. So on the x-axis, the timing, on the y-axis, the control structure of the application. You can see here there is a main function. Here is an edge toggle step. So this would be one step of the whole application. And on this level, we basically can see the individual elements of the original model. We have a look at that again. So the two larger ones would be the convolution here, product, add gain, something like that. So we can see here these function calls, we can see the MATLAB functions, but we can also see that here there are only some for loops. These for loops here are not, so the smaller blocks here, like the product and add, are not represented as function calls, but directly converted to for loops. And now if we have a look at our application, the idea is to find the critical parts. Okay, these convolution parts, these two function calls take a lot of time. Next one would be here, one for loop of the calculation. You can also have a look at which part of the code is it. Okay, this for loop here, okay, it has a square root calculation. Okay, we know square root of a value here is more complex. Yeah, this takes more time. Optimizing square root might be an option, but now just start with the larger blocks. Our tool automatically performs a task level parallelization just by looking at the tasks that are available. And if you have a look at this function, yeah, we can see this function call, or both of these function calls are dominated by one larger for loop. And we can also already see, okay, the individual parts of these for loop are executed, are scheduled in parallel. We could already guess so just by looking at this model. These two are in parallel here, and yes, they can be executed in parallel automatically. You can see this would lead to a speed up of almost 1.4. So we are using, well, 2 cores out of these 4. This is not very much. So the next step now would be, okay, task level parallelization is not really enough. We want to increase parallelism of this program. Increasing parallelism, we have these code transformations, and these are indicated by this icon here on the top right. And if I just right click on it, I can see create transformation. So here there are a few available. The first one, create kernel. This would be an optimization for GPUs, so creating a GPU kernel. This means extracting a part of the program that should be executed on a GPU generating CUDA or OpenCL code. The extraction is possible for each target platform, although here for the Raspberry Pi there is no there is no actual OpenCL compiler available for the graphics for the GPU here. So on that target platform, it's not the best one. The other ones here are optimizations of the actual loop. So loop tiling is an optimization that can increase the data locality, increase the performance. Something like normalized loop would be to shift the boundaries of a loop. So you can see here, this loop starts at 1, it goes to 481, but normalizing means we can start from 0 to 480 so that every loop has the same format. Loop unrolling means instead of having one iteration after the other, so only with an I++, we are able to make a loop unrolling with a factor here from 1 to 480. So instead of executing one iteration with a loop with unroll factor of 2, we would be duplicating the body of the for loop and could execute 2 of them in one iteration. And just duplicating this doesn't really increase the parallelism, but depending on the actual program, if there is more code, it might be possible to detect independent parts in these larger copied body blocks. For this example here, we want to use another optimization. So this is an optimization. We can optimize the overall function here for different numbers of cores. If I just apply this for 2 processors, we can have a look at what happens. Basically here it's an integration or it's an interaction between code generator and Parallel Studio. So it's also possible to perform code transformations as part of the code generation part. And now we can see we optimized this function here, and yeah, instead of having this one loop, we now have 2 loops, and these loops are independent from each other. So dependencies here are highlighted by color. So if I click on this, we can see this one is highlighted, so there is a direct connection between them. So this function here or this block has to be executed before this. Here there are no actual dependencies, so these can be executed in parallel. If we have a look at the parallelization, we can see now, okay, we are now using 3 cores, so the automatic algorithm detected that these 2 smaller parts can be executed in parallel. But you can also see that the actual runtime wasn't affected too much by this one optimization, but this is only because we only optimized one of the function calls for 2 cores. The other one is not optimized, so this is still a longer block here, and we can see there is a gap, and we have to optimize the other function call also for at least 2 cores to get a better performance. So let's just do that. If we also apply this transformation here, both of these functions should now be optimized dominated by 2 independent for loops, and you can already see, okay, now all 4 cores are doing something. There are no additional gaps, and the speed up was increased by a bit. You can also have a look at speed up of individual functions, and we can see the speed up of these convolution functions here is at almost 1.9. So for 2 cores, this is already quite good. But as this is only a part of the overall main function, we can see the speed up is smaller for the whole application. And yeah, after optimizing these 2 function calls, the next one would be optimizing this one. So this is square root calculation. There are several implementations, so here it's possible to change the implementation, for instance, to get more performance out of that. But just for the sake of demonstration, you can now assume, okay, this is a good parallelization. Then we can just press the button Run Code Generation, and it will automatically generate parallel C code for this kind of parallelization. Parallel C code looks something like this. You already see at the beginning of the file, there are now convolution functions that have different endings. So we have here a version for processor 0, processor 1, 2, 3. So we can see, okay, there are different versions for the different processors. And they also have differences in the number of arguments. So the first one here has 3 parameters, the second one only has 1. So these are really individually parallelized for the different cores. So if we look at these P versions, so convolution P0, here we can see also the variables are now core local, so also have an ending of P0. And we can see that there is explicit communication here inside of the program. So here we can see send H data P0 from core 0 to core 1, and this also from core 0 to core 1. And so for the other core, basically receiving this data is the first step. So everything that is related to this communication, synchronization of programs is automatically generated and part of this parallel-C code. Now going down further below, we can see we have here a main function, and the original program was a normal C program that had a main function, so it was int main, and you're basically calling here one other function. But for the parallel program, we can see now that there are several main functions. We basically have now a main function for each core. Each of them will call their individual emmtrix step function. You can see here, this is also a parallelized version, so some data is sent around, some calculation is done here. And just to start now the parallel program, we used a template system. Look at the generated files. We have the parallel code now. This was the emmtrix, so the main C file, but now we also have an ex main C file. This is a file that is generated automatically, and this would be the default case. We have then one new main function. We have an API just for the initialization, and the initialization will basically split up the program, and then we have this run main function, and depending on which core this run main function is called, it will, here in this switch case, call the correct main function. So main P0, 1, 2, 3. And as I mentioned, this is a template-based system. So here we basically have a file that can be edited, so to fit the actual environment that you want to use it in. So if you have a special operating system, if you need some specific tasks, you can just modify this file, and the C code will be generated in a way so that it can be called from here. This flexibility here is also available for different other things. So we have not only the generated files, we also have the target platform. The target here, so in this example, we were using the Raspberry Pi. You can see here the platform Raspberry Pi. We have several files here just for the hardware model. This would be a table for the communication overhead. Here there is a description of the actual hardware that is used, and all these parts here can be customized for different target platforms and for different setups. So we are really able to combine different architectures. We can define the communication overhead. So this is also usable not only for communication on a single processor or single chip, but also for larger systems that are connected using Ethernet, for example. Yeah, I think that's the basic idea of the whole workflow. So if the hardware would be available, we could send it now over, execute it there, get some performance numbers back just to evaluate the actual performance on the target platform. You can also perform some parallel or sequential program tests just to check that the sequential C code behaves exactly the same as the parallel C code. And this is something that we are also extending with an additional checker tool that ensures that the functionality of the parallel program is identical to the sequential program, and the only differences that are allowed are code duplication and is the use of our API, so having the communication as part of the program just to handle the data dependencies. Okay, I think that's it from my side. Are there any questions or comments on this demonstration?
All right. Well, I haven't got anything in the chat. We're more or less come to the end of the webinar. This is what we wanted to show you. Just giving you a little bit more time to come up with a question. But, well, for now, I can say thank you for attending. As I mentioned earlier, I will send you a brief questionnaire. It'd be nice if you could send it back to us with your opinion. That way we'll get a little bit of feedback from you and can see what we can do better in the future. All right. I think there's no question coming. I don't hear sort of any noise in the chat, so that's okay. Thanks for spending a bit of time with us. I think well, we'll just have to say goodbye to you now with the last slide, Oliver. If you find that one still. That's the one. Okay. Yeah. All right. Thank you from the team. Thank you from Karlsruhe. Have a good week. And I'll send you a quick email. Yeah. And hope to talk to you again at some stage. Yeah. Bye for now then.
Also, thank you from my side and goodbye.
Goodbye.
Thank you very much. Goodbye.
Yeah. Thank you, Nikolai. Bye-bye.